Welcome to the first meeting in, 2.5 years. Okay, I'm Barry Grossman, the Secretary-Treasurer of the New York chapter. Ari Rentals, thank you for making space available to us. So SMPTE-New York works with sponsors. We have our sustaining sponsor, B&H Studio. Then you saw on this slideshow a bunch of different sponsors, Friends of SMPTE. And the Friends of SMPTE basically, you can talk to me, talk to other members of the Board of Managers. Basically, our goal is to run these chapters self-funding. So you can talk to myself, just contact anyone in the Board of Managers. Membership, who's currently a guest visiting today? Welcome. There's some cards out in front. You can talk to us. There's currently a discount if you want to become a member of the chapter. You have professional, executive, students. If you're currently a student, there's I think it's $15 a year. If you recently graduate, $49 a year. It's a great way to meet people and learn more about the industry. There's some active student chapters in the area and some that we're looking to grow. If you have any questions, talk to me and talk to anyone else that's currently wearing something like this. We're here to help you out. In addition to working in the industry as a video engineer, I'm also an adjunct at CUNY City Tech, and there's also other professors here. Ari Rentals, thank you for inviting us to your house. And David Weiner, who's the producer of tonight's meeting, and we'll take it from here. No.
Can you all hear me? Good. This is a very special evening. This is our first in-person meeting in 2.5 years. So tonight we're kind of inaugurating the next phase of SMPTE-New York going forward. It's a special meeting because this is our first meeting in this new facility, and we have Ari Rental to thank for that. Andy Shipsides, who's the president of Ari Rental, would have been here tonight. There's illness in his family, but I want to thank him anyway. He was instrumental. He was out of the country, and he was still helping to organize this event. Peter Crithery, are you here?
I am.
Peter, I want to introduce you to Peter Crithery from Ari. He's going to say hello and make a few remarks.
Thank you. Hello, everybody. Welcome. It's a distinguished pleasure to have all of you here. Is everybody excited to be here? Yes? What do you guys think of the facility? Pretty amazing, right? Yeah. It's what? That's a marketing campaign right there. Yeah. Yeah, on behalf of Ari, I'd like to welcome all of you here. As David said, it's the first time you guys are getting together in some time, and this is actually the first time you guys are here in terms of an educational event at this facility. So you guys are the first. So that's also really, really cool. One of the big pillars of Ari is education, and you're going to find that pretty much every month starting in January, we'll be having activities here in this creative space to be educating, engaging the community on all sorts of different topics, creative, technical, operational, and so forth. So we're really looking forward to doing that. Thank you, David, for being here and helping to arrange this evening tonight. I want to thank the special guest, the presenters that are going to illuminate all of you here. Very, very bright presenters that we have here tonight, given all the lights that sorry, bad joke, right? Okay. Okay, nobody's laughing. Okay, all right, fine. All right, so with that, I'm going to hand it back. Again, thank you very much for coming, and have a good evening, and hope you find it informative and educational. Thank you very much.
Thank you, Peter. There's another person here at Ari Rental who was absolutely instrumental in making this evening happen, and that's Mike Sippel. Mike, are you around? Over there. A round of applause for Mike. Without whom we wouldn't have the generator outside, which was generously donated by Insight, so that's something. Now, it is a special evening tonight. I don't know if you all realize how lucky you are to have all these lighting instruments. nearby where you can play with them. And after we finish, there'll be a few minutes where you can go up and talk to the various presenters. These lights over here, designed by Vittorio Storaro and DeSisti. You may know who that is, the DP who shot Apocalypse Now and many other, The Conformist, many other classic films. The ARRI Orbiter, which is has a 6-color phosphor light engine. Prolict, which also has a 6-color phosphor light engine. And on the far end, Cineo, which has the most remarkable focusing mechanism, which Brian Doran is going to show you, and that's one of its 15 tricks. These lights in here are the future. In my generation, it was tungsten halogen. It was wearing heavy gloves so you didn't burn your hands. It was planning for air conditioning in any interior space you shot in. It was doing tie-ins, or going out in the street and stealing electricity. It was whatever you had to do, bringing generators, anything. But you needed a lot of power. It put out a lot of heat. You know, the talent by the 10th take, you know, was sweating. And so was the crew. And I'm not exaggerating. You're not in that world anymore. You're in a world where you can dial in any color you want from these 6-color lights, 6-color phosphor lights. These are bicolor. The DeSisti lights, you probably all know about lights that can switch between 3200 and 5600. The point is, all of these lights run on a standard 20-amp circuit, with the exception of that giant light back there, which draws only 2,250 watts, and anyone that knows electricity knows that you should be able to plug it into an outlet, because an outlet will get a 20-amp, will give you 2,400 watts, except that pulls a lot of power when you first turn it on, and it will break, you know, the breaker will flip. I didn't know that, see, so I learned something tonight too. So that's plugged into the generator outside using a stage pin, you know, 60-amp line. But regardless, all of these lights use dramatically lower power than in the past. They don't put out the heat. You can work with them all day. The talent doesn't get hot. You don't burn your hands any longer. You don't need gels for the most part. It's just, you guys are going to have a walk in the park compared to what we had, but I'm happy. I use these lights too. I have already done a feature with one of the lights in this room. And it's just, again, it's an amazing time to be starting out. I see a lot of young people here. It's an amazing time to be starting out. So that was the reason I wanted to do this evening. And I was very lucky to get Brian Doran from ARRI to do a presentation on the orbiter light, the ARRI Orbiter, which is that one right there with the projection optics on it. Mitch Gross, who's here from Prolict, he's got the light over here, which also can have projection optics, and he'll talk about that. Paul DiStefano is here from DeSisti. He's going to talk about these shaped lights, and there's 3 over there, but there's 7 more of them, and he'll tell you different shapes, and he'll tell you about that. And Chuck Edwards, who's here from Cineo, and he's going to talk about this light over here, this big ellipsoidal mirror light, which is an open-face light, which has something in the center that we can't figure out the name of. I mean, he calls it a tower, some of us call it a corn cob, I don't know what it is, but he's going to talk about what that is and how it functions. So I want to go in alphabetical order, which means that we're going to start off with ARRI, and Brian will go first. So again, thank you all for coming, and let's get going. Now, if you have questions, feel free to ask in the middle of the presentations. You won't be rude by interrupting and asking questions. At the end, if we have time, we'll do further Q&A. And if you guys don't have questions, I will. So with that, Brian?
Thank you very much. Just setting up my my laptop. I know we all have some presentations, so bear with me here. All right. So thank you very much. Thanks for coming, and to all those watching at home on YouTube in the future, the near future. So my name is Brian Doran. I'm the product specialist for ARRI Lighting. So I'm sort of the in-between of product management in Germany and the Americas marketplace. So I like to tell people, you know, if you have any technical questions or complaints or requests, that's what I'm here for. And so today I'm showing off the Orbiter. It's a light we launched about 2 years ago, but we have some recent updates in terms of optics and software that are really interesting. So the big picture of it is that's this LED point source. Before this we had the sky panel, which was rather popular, and that was a soft LED light. That was RGBW. It's a warm white. The orbiter is now a hard source, which is red, green, blue, amber, cyan, lime. And so the sort of game of it is that you change the optics. There's this quick lighting mount that lets you, use open face, soft boxes, or more recently, things like Fresnels and projection optics, like ellipsoidal style optics. And so what powers this all is that spectral light engine, that RGB ACL light engine. And by having that bigger mix of LEDs, we're able to get a better quality white first off, for your typical applications. We're also able to get saturated colors and pastels, which is something that's hard to accomplish with an RGBW light source. And so here's a sort of detailed shot of the light engine itself. You can see those 6 different diodes. They're those chip-on-board LEDs that are becoming very common in the last few years. Before that, it was surface mount packages. And this is a comparison to a previous LED type of point source of ours, the L10. Some of you might be familiar. That was the biggest of our LED Fresnels. And so that was an older technology. It was RGBW. And in order to get a type of point source out of it, we had this big light engine. I mean, this TV screen's not that much smaller than it actually was. It was really quite large, almost like a foot in diameter, this light engine. And we would have to have a collimating lens on it to focus all of the light onto a little source, maybe the size of my palm. And then that would become the source, and we'd shoot that into a Fresnel, and it worked. It got really good shadows, but optically that's very inefficient. And so with advances in technology, with the orbiter's spectral light engine, we're able to now start with a light engine that's about the size of a silver dollar. I guess if you take Metro North, you've probably gotten silver dollars and change.
Hey, Brian?
Yeah.
Can you explain what RGBW is?
Yeah. So RGBW is red, green, blue, and white. That can be a warm white that's balanced to 3200 or a cool white to 5600. Usually those white LEDs are produced by having a blue pump. It's a blue LED that excites a phosphor coating, and depending on the makeup of that phosphor, it will, emit a different color temperature. And the benefit, yeah, please.
So sometimes you have RGBW.
That would be when someone has a warm white and a cool white LED. Yeah. So that way you have a good color rendition and I guess a bright fixture for 32 or 56 or higher or lower. Well, one of them is white that's balanced for 3200, and the other would be white that's balanced for 5600. Or it could even be 2800 and 6500, just so that you can fill out that spectrum more completely.
Brian, did you mention the 6 colors?
Yeah. Oh, yes, good point. The question was, I think the question was, why are some fixtures RGBWW having 2 different white LEDs in them? Yeah. Does that answer the question?
So it's more accurate.
Yeah, exactly. The whole game is to try and get a more accurate color. And I have a slide later on that touches briefly upon the different metrics that we've used to sort of describe how accurate light sources are. But I guess stay tuned. And so because the orbiter's using that red, green, blue, amber, cyan, lime, we're able to have a really accurate color, and we're also able to have a really wide range of colors. And so on the orbiter, we can go from, I'll do it on this spot behind me as well, 2000 degrees Kelvin as our warmest white color, which would be, like a tungsten unit dimmed really low down. How they tend to warm up as you dim them. And I can get all the way up to 20,000 degrees Kelvin, which is, beyond what would probably be occurring in the natural world. Like if, overcast skies, 8,000 or some, in that range. But we can go all the way up to 20,000. So I guess that's to say if your camera was white balanced for something cooler, you could still get a really cool white. So I'll park that back at 56. So this is the gamut of, well, right now this is just the CIE chromaticity diagram. If anyone hasn't seen this before, this is basically a chart that shows all of the colors the human eye can see. I mean, there's better ones that show like brightness values too, but this is just like a relatively straightforward chart of all the different colors the human eye can see. It's called the CIE 1931 chromaticity diagram, and it's something that I think a lot of us manufacturers are now referencing when we're letting users pick out colors or when we're describing colors. So that black line on there is the black body locus. That is the line that basically represents different colors the human eye can perceive as white. That's sort of the interesting thing, is there's a whole huge number of colors that our eyes willing to accept as being white. Then the large white triangle there is the Rec 2020 gamut. Before that was Rec 709. That's like the color space or gamut that your projects could be delivered in. So Rec 2020 is a much newer one. I can't personally speak to how far on the deployment of that we are, but then if we show this blue shape, not quite a triangle, this is the gamut of the orbiter. And so we're able to cover 90% of that Rec 2020 gamut and are much larger than the Rec 709 gamut. So we're able to, create these colors that will, a very wide range of colors. And so earlier we sort of were touching on color rendering. CRI, which I'm not really a big fan of, that's the original one called Color Rendering Index. That's taking a measurement of 8 chips of like kind of pastel colors, and then you would get a score from 0 to 100, how accurate your light source matched an ideal light source, which was basically a tungsten light. So the orbiter has a CRI score of 99. Then there's TLCI, that came later, and that was devised as color, how a camera sensor would see it. It wasn't like a CMOS camera sensor though. It was one of those, it's like a tri-prism, these 3 prism cameras, CCD, was that what they were called? Yeah, so I don't know. It's better than CRI, but I personally am a big fan of TM30 it says 15 here, but there's been a revision, TM30-18. And so I have a pair of TM30 charts here. What this is instead of just 8 little chips to measure or 15, it's 100 different chips that are being measured. The benefit here is that, frankly, it's harder to cheat. With only 8 samples, all the manufacturers knew where they had to perform well, and you could get a light fixture that had a great CRI and then looked terrible. So with 100 different chips, it's a much more well-rounded test. And there's also some really interesting things that come along with having this like vector chart. The simple part of it is this RF score on the top left. That's kind of the equivalent of what the old CRI score was. That's the fidelity. So if it's 100, it's a perfect light in terms of color rendition. It looks like it's supposed to. If it's like 70, that's maybe going to start getting your colorist mad at you. On the top right is the gamut. That speaks to how much the light, whatever you're testing, might oversaturate or undersaturate. For us, we probably want it to be as close to 100 as possible, but this metric also takes into account industries like retail, where they're like, yeah, who cares? Make it as saturated as possible. Research shows customers like that. Well, what's also really cool is we have these slices of the vector chart, so you could even see the particular areas where there might be deficiencies. Like you could see, okay, there's a huge saturation in purple, so I know this light's going to skew magenta. Or there's, almost no red. You can kind of get a better sense of how the light's going to misbehave, and if you're willing to accept that. You could also see sometimes that instead of an arrow in or out, it'll have an arrow along the rim of the circle, and that would mean there's color shift. Like where it should have been green, now instead it's going to start looking blue or something like that. And so this is just I fully endorse the TM30-18 metric. Demand your manufacturer start supplying that instead of CRI, I guess. It's just I think it's a much stronger one. There's also one called the Spectral Similarity Index. I don't have a chart for that, but the game with that is that you could take the spectrum of one light source and overlay another one, and you could see the areas in which they're different, and you'll get a score for how close they are. And that's cool because you could also match to, some like fluorescent fixture that you have to match to, other things like that. So another really important thing with the orbiter is the calibration we do. Basically, every unit that goes through the factory gets individually calibrated, where they'll run it through a range of temperatures and make sure that they're all performing to the same standard. Normally, I guess, like the first line of defense for making a good light is by having good binning, where you'll accept LEDs that are like within 10% of each other, or 5%, or whatever you're willing to pay for. It's really expensive. And so we also do calibration to get everything to match. So the fixture you bought 5 years ago is going to match the one you bought today, and it's going to look the same if you're shooting on the desert or if you're shooting, in New York in the middle of the winter from our calibration process. Our L70 time is 50,000 hours. This is actually something it's a metric that's thrown around all the time, but I don't think is ever really talked about so much. When someone says a light's going to last 50,000 hours, that is the L70 time. That means that after 50,000 hours, the LEDs will be emitting 70% of their peak output. And so, it's not even really even. Like, the green might age at a faster or slower rate than the red, and you'll get color shift. And frankly, I think most lighting fixtures will have power supply failures before 50,000 hours is reached anyway. So, there's something to the 50,000 hour number, but I don't know that it tells the whole story. So that's sort of why we are very careful with our heat management. We have a lot of a heat sink technology going into it. There's heat pipes pulling away. There's the fan, trying to keep everything cool, because as much as LEDs don't produce heat, they also don't deal with it very well at all. And if they begin to warm up, they'll start to really suffer. Oh, I'm sorry. For the recorders, the question was about how long the LEDs will last, like the drop off, right? I think you had your hand up first.
With the six-color engine,
Mm-hmm.
is there any drop-off at all in any of the spectrum, like there were in some of the early LEDs?
It's filled in. So the question about drop off in the spectrum now with the 6-color light engine, and it's really much smoother than it used to be. With every new LED added, you can try and smooth out that spectrum a bit more. Yeah, if you've got like a Sekonic C800, you could take a measurement of the spectral power distribution. It's this graph that just shows the whole sort of output of a fixture, and you don't want it to be peaky. As smooth as it is, or the smoother it is, the better. I think he had next.
Yeah, going back to the color metrics.
Mm-hmm.
We also television have a consistency index.
Yes.
Came out of the KSR report correctly. SSI, Spectral Similarity Index, came through the Business Signal Committee.
Yeah.
Where did TM30 come?
TM30, so the question was about who developed TM30-18. If memory serves, that came from the IES, the French acronym I can't remember, but it's sorry, the Illumination Engineering Society. Thank you.
General Illumination Engineering, not specifically. So I believe they use TM30 in architectural lighting.
Yeah.
Any illumination industry will use TM30.
Yeah, it's less tied to our industry. Yes.
You said 50,000 hours. Give me it in the real world. If I use that light every day on a shoot for how many years I might get from it? Just trying to get.
Well, we have L7s from 2012 that are in a studio that never shuts off, and they're still working. So I don't know. I tend not to put too much value on the 50,000 hour thing. I guess yeah. Yeah. Oh, I'm sorry. I think he has his up first.
Is the light engine replaceable?
Yeah. Yeah, with all of our products, you can replace the light engine. It might not always be like super simple, but we have service centers and we can always exchange parts. We try to offer those parts for as long as possible. Like, I used to be in service and still routinely repair ballast from the 90s, so we try to offer parts as long as possible. Yeah, I think you had a question?
I know it's not a lighting question, but
Okay.
does apply to the camera sensor thing?
The 50,000 hour
Yeah.
thing? I don't know what the metric is for camera life. I don't think they do the same L70 thing because it's not like a light emitting sight. It's a, yeah. A question for my colleagues. So another interesting thing about the orbiter is we have this color sensor. So there's a small spectrometer in the fixture that lets you capture ambient temperature and reproduce it out of the light engine. It will also give you an XY coordinate of what that color is in case you want to replicate it. That was that chart earlier, the CIE chart. Just a really precise way to describe color where HSI or something else might not be as useful. Yes. How accurate is it? The XY or like in general? Quite actually, like a few minutes before this, I was doing a little cross check with my Sekonic where I plugged in an XY coordinate on the orbiter and then I measured it and saw what the Sekonic gave me. And I think I was within like maybe 5/10,000ths on the X and like 2,000ths on the Y. So I'm pretty happy with it. Yeah. And so here's what the sensor mode UI looks like, where you can do a continuous or a momentary sort of snapshot of that ambient color and reproduce it on the orbiter. You could daisy chain that to another orbiter and run them in host client mode, or you could just like grab the XY value and, you know, put that through your console or onto another fixture, whatever you want to do. And then another aspect that was really important to us was the low end. That's really one of the hard things with LED is to get good dimming. You know, you could have fixtures where it sort of snaps out at the bottom or we get color shift. And so that was something we focused a lot on, was getting a really good low end. So I'll just bring this fixture out. I'm at like 22%. Whoops, sorry, that was me. I'm at around 10% now. Down to a 6%. Down to 5. There's still something there. And it's getting hard to see now. Down to 3, 2. Here, I'll stop at 1 and just sort of put my hand in front of the fixture, and you can still see there's a little bit coming out of there. So that was something really important to us, was to get that good dimming curve and not have it sort of pop out or get crazy color shift. Yes?
Are you doing the dimming by pulse width modulation?
We use a mix. It's, I would say, primarily pulse width modulation, but on the very low end, we have to do a little secret sauce type of mix.
What's the frequency of the pulse width modulation?
Industry secret.
Well, because I'd be concerned that with a high-speed camera, high frame rate camera, with that beating with the frame rate.
Yeah, with high speed, we've tested up to 25,000 frames per second on the Phantom and haven't had any sort of issue. Then there's also a sync mode, which we've implemented recently via software. So there's a sync mode, I'll go quick. You can synchronize this to your camera shutter and only have the light emitting when the camera sensor is exposing. It saves like almost 50% of your power, so some good cost savings there. And then we'll get on to the actual projection optic. So I've got a 25 and 35 degree projection optic that's made in partnership with the same company that makes our Signature Prime camera lenses. So it's really a super precise projection optic, almost entirely free from chromatic aberrations. And I have it set up this way to show that here I have my beam edge is quite sharp at the same time as my shutter edge, which is something that's really quite difficult to achieve with an ellipsoidal. Usually it's one of the others in focus, or you start getting the really bad chromatic aberration where one of those edges has got like that red, brown, or blue color to it. So we're able to avoid those sort of pitfalls. There's a motorized focus in this, so I could play with that. And so you can bring that in and out from the optic itself, from the remote, or via DMX. And it takes standard B-size gobos. This is just a little, you know, what we're used to versus what we're able to do here. And before I move on to the Fresnel, I want to show something that I think is really pretty neat. I'm going to put the microphone down and hopefully it doesn't, feed back on me. One of the really hard things to do with a projection optic is to get like that razor thin cut. And so let me just open it a really small amount. And we're able to get that really thin blade without it just becoming a mess of blue and brown chromatic aberration. So really quite happy with that. And since I'm running low on time, we'll have a chance after this to check it out and run it through its paces a little bit more. The other optic, I don't have time to swap it on, but we'll hang out after this, is our Fresnel. It's a 15 to 65 degree, sort of like a big eye Fresnel. That also has a motorized optic, just like the projection. So you can run the zoom via DMX if you want to, or from the control panel. And because we go all the way out to 65 degrees, you're able to get a super sharp shadow from it. I think our previous Fresnel, the L10, went to about 48 degrees on its maximum beam angle. And that takes, the standard M18 barn doors or T5 barn doors, ST2 barn doors, the stuff you probably already have in your inventory if you're a rental house. And what's neat, you also have a little readout of the focus, or rather the zoom angle. So if you need to replicate that at a later date, you're able to do so for your reshoots or whatever your need might be. And the last thing really quick is a docking ring. Of course, everyone has a whole warehouse full of an existing 3-letter company's ellipsoidal barrel. And we've created a docking ring, so if you wanted to use something we might not have, like a zoom or a 50 or a 19 degree, you can use this docking ring as an adapter to use your existing ellipsoidal type barrels. And I think that brings me to the end.
Brian, how long would it take to put the Fresnel on it?
Not long at all. I'll do that really quick. That's sort of the feature, I guess, quick swapping optics. There we go. Don't want that thing rolling off the table. So there's this little blue button. You just push that in, and then turn it. The optic pops out. This looks heavy, but it's actually extremely light. So I tend to make everybody hold it to see what it's like. That's like the price for the demo. You have to pick up the Fresnel. Yeah, really easy to swap that optic. So here I'm at my full flood at 65 degrees, and I can pull that into 15.
What percentage are you on?
Right now I'm at 100% intensity. Cool.
What's the lowest intensity percentage?
Well, I guess 0. I could. I'll go out again. Yeah, I'm seeing more and more where we talk to customers. They're like basically working below 30% for the whole show as the cameras get more sensitive, and so that's sort of the concept with this.
You're a little kid lying in bed at night.
Yeah.
You're trying not to have nightmares.
Like we just did our whole LDI booth. I think our brightest fixture was maybe 65% intensity.
Bring it down further.
Here we go. So now I'm at like 13%, 10%.
Okay, stop there.
Yeah.
Put your hand in front of your face so we can see the shadow. You all see how it's very even.
Yeah, we're not getting that crazy color shift that was happening in like early LED technology. Here I am at like 4%. You might still be able to see that. Yeah, so that's increasingly the game, especially with the new Alexa 35. Don't need so much light.
Just to confirm, that's full flood, right?
I'm in full spot right now.
Full spot.
Yeah, 15 degrees. And I'll just bring that all the way out then. Here's like 0.1. I mean, I can see it if I look at it, but I don't know that it's making it over the way over to me. All right, very cool. Are there any questions before? I'm probably like out of time, but.
Bring it up and like yourself, and we're going to use that for the next speaker.
All righty, sounds good. Do you want it?
That's perfect. Bring it down a little bit. About there. That's good. Thank you.
It's an honor. All right, thanks everyone.
So Chuck Edwards from Cineo, and he's going to show the Reflex 15. And my question is, why is it called Reflex?
Yeah, it was because it was actually the engineering name. We originally started with Tin Man as the name, and then we started calling it Reflex because it was a reflective light, and it just stuck. We didn't expect it to actually that to be the final. pulling up the presentation. I'm going to start with a demo on the light and explain how it works. Just want to make sure the presentation looks up, and then I was going to actually, because this is a great crowd, I love talking to engineers. I want to do something really techy and kind of explain to you how LEDs break and actually work. I come out of the LED development side. I worked for a long time in LED R&D, in materials R&D. And so I wanted to talk about that a little bit too. So that said, let's go to the reflex. Right now I'm running at 1%. We also find, because the lights are getting brighter and cameras are getting better, 1% control, where you have control of the CCT or blended color at 1%, is now critical. People are running at those low percentages all the time. So the idea we came up with this light is first, and we'll explain why, the LEDs, to get a unified source, we love the idea of a single source. To keep a single source and make it that intense, what you have to do is cram so many LEDs into a small space because of the concept of E-to-do, which basically means the size of your reflector is a function of the size of your source. Tiny source, you can make a tiny light. Big source, you have to make a big light. So what we want to do is make the smallest source we could, so that's why we use liquid to pull the heat away. And what you'll see is, rather than do mechanical focusing, we have 9 rings and we can decide which ones are on. So if you can see the rings, what I'm going to do is show you how we focus a beam. So here we're going to go to a 15-degree beam, and then you'll watch as we go to a wider beam angle, what we're doing is we're actually lighting up incrementally down the tower. And what it is 1, 2, and 3 are right in focus of the parabolic mirror. Zones 4, 5, 6, 7, 8, 9 are continually further out of focus. So basically you have the ability to either put all your light in a focus location or move your light. So it's the same thing you do with a traditional PAR, except you're using a crank or Fresnel. You're cranking the light, you're moving the lamp. Instead, what we're doing is we're just activating different parts of the zone. The advantage of this, though, is, of course, we can go instantly from one to the other. And you can do, whether you want to do paparazzi effects or whatever, we can control any zone. And then we even give the ability to the user to paint the zones. You can actually build your own beam. The other thing we can do is, in every one of those rings, we control the CCT. And as a result of that, we can do something a little more advanced and funky, which is, I can say, all right, I want to have all of them on, but I want to change the CCT by zone. So here I'm making a cool center and a warm edge. So we have filmmakers that decide they want to have a specific look. Now, I've been running the light at 1%. So what I wanted to do is let you actually see the light actually powered up. There's no, I was trying to, yeah. So this is a 1,500 watt light. So as far as LED, we wanted to do something that could plug into any stinger, but that basically we maximize the power. And so I can go from 2,700 to 6,500, and I can go to a really wide spread, or I can go down to, it's actually slightly below 15. And then the most unusual part about it is I can touch the lamp. So when I'm at trade shows, just to freak people out, I take Windex and I clean the lamp while it's running. And anybody that's worked with HMI or tungsten, they just can't believe it. And we've hit this with a hammer. It's polycarbonate. It's really tough. So that part of it's good. So that said, let me go on to the presentation, which is really going to talk more about LED technology and why we took this approach. So you have a basic mode where we choose the beam shape for you, where you can just say beam angle, CCT, and intensity. Or we've got an advanced mode where we give you control of each ring. And you have 9 channels of intensity and 9 channels of CCT. And so you can either control it down to the ring, or you can control it more like a traditional light. If you go to the Apple Store, the App Store, it's called Cineo Stage Links. It's free, and it'll let you reproduce the exact same touchscreen on the back of the light is on the app, and it's available for Windows, and it's available for Android, and it's available for Mac. We write one code base that goes on the light. The light's actually a Linux computer. That same code base runs on any of the major platforms. We can cross-compile it, and you can run it anywhere. So our goal is that you could run the light on whatever surface you want to run it on.
This is a computer with a light attached.
This exactly. And I'll tell you which, it's a Raspberry Pi 4. Raspberry Pis have gotten so powerful. It's a Raspberry Pi 4 with an HDMI screen on it running Linux, and we cross-compile to all the other platforms.
Chuck, could you explain CCT? You mentioned that, and maybe not everyone understands that acronym.
The correlated color temperature. So it's basically is the light cool or warm? What most people don't know, and I don't want to run over on time, but I do like the nerdy stuff. So incandescent lights actually, the temperature is the temperature of the light. What Thomas Edison figured out is if I make something 2,700 degrees hot, it glows 2,700 degrees Kelvin. I mean, that is the temperature. The reason why you can only make a tungsten light up to 3,200 is tungsten filaments melt at 3,600. There is no metal that you can heat up past 36. So incandescent light, the color temperature actually is the temperature that thing is, how hot it is. LED actually changed that, and we try to mimic those same spectrums. That's where the number color temperature came from, or CCT. So LEDs, first thing I remember, Sir Isaac Newton said this, you can change energy from electricity to light to heat, but you can't get rid of it. It doesn't just go away. So if you spend it, it's got to go somewhere. So the reality is LED's pretty efficient, but it's still generally mostly heat. So if you look at this chart, if you have an LED light, you're going to use about, this is our 1,500 watt light. You're going to about 225 is going to be heat coming out of the power supply. 765-ish is going to be heat coming off the LED dies themselves. And then you're going to get about 510 watts that's actually radiated light that hits the subject. So you're still losing 2/3 of your energy in heat in an LED light. But the advantage is you're generating a lot more light as far as a percentage. Now, in the case of tungsten, you got less than 5% of the energy out as light, and you got 95% as heat. So it's still way more efficient than the old ways of making light. But you still got a lot of heat to deal with. Now, the problem is LEDs on the top have a silicone cap. That's the lens or the cover. And so the actual semiconductor that turns electricity into light, that's a crystal, and that's a pretty robust thing. But when you encapsulate it in this clear plastic, that's what's going to break. And 90% of your time when an LED fails, it looks like this. It actually burns the plastic right at the top of the LED. And this is what we're trying to avoid. As a result of that, almost all LEDs really have a maximum temperature of 85 to 105. If you ask the manufacturer, how hot can I do it in centigrade, they'll say between 85 and 105. And the cooler you get it, the safer it is. And what will happen is if you get hotter than that, this type of browning and damage occurs. So I have the Chuck Edwards 2-second rule, which is I can hold on to something that's 60 degrees C for 1/1000, 2/1000, then I'm uncomfortable and I let go. So if you go over to an LED light and you calibrate your hand after a couple of experiments, you can touch the hottest part of the light and you should be able to go 1/1000, 2/1000 and still be able to have your hand on it. If it's not, it's probably hotter than 60, and then that means that the dyes inside are probably getting hot. And so the problem then is LEDs have to be kept relatively cool. So this is an IR image of the tower running at worst case scenario as hot as it got, and the middle top of the tower, which was the hottest spot, got to 61 and it was fine. So when we're designing lights, and most people wouldn't share how they design the lights, but I wanted to get you an idea of how people attack the problem. If you're going to build a big soft light, and you're going up to 75 watts per square foot. Now, the great thing about making a 4x4,
is you got a lot of square footage. You got 16 square feet. You can use up about 75 watts per square foot and not actually have to add fans or do anything exotic. Pretty much a big flat metal thing using 75 watts per square foot can cool itself. You go to 170 watts, 50 to 170 watts a square foot, now you've got to add fins, and you're going to notice that. You're going to see the next level of hard light, or LED lights you get, they're going to start throwing aluminum fins on the back or some type of heat sink. And that's because the surface area of it being flat's not enough. And that's what this light was that we did. When you get over this kind of power and you're trying to build a 1x2 light and you're in the kind of 100 to 350 watts per square foot, then what you're going to see is people are going to start putting fans in the product. They're going to have heat sink fins and they're going to have a fan, and that's the way you cool it. And independent of the optics, the thermals is the same for everybody. You've got to get air to go across the product, and it takes so much surface area of metal and so much air passing over it in order to cool it. What a lot of people don't appreciate is most LEDs, the primary size is the package. The LED chip itself is tiny. So you'll see it's possible to cram a lot of LEDs in a small space. The reason that matters for us is if we want to make a hard light, we want to get as many LEDs in the smallest space possible. That lets us make a really nice clean optic and a really nice clean lens. So what we're trying to do is say, how can I cram as many of these LEDs in the tiniest space possible and still not burn them up? So the way you'll see tried is one approach will be spread the LEDs out and put a separate optic on every LED. The reason you do that is it lets you cool them in a spread out way. This works for cooling. The challenge is that you do have separate sources, and you've got to set and match that, and it creates a different type of shadow. The other option is you do something like this, some complicated heat sink, and you put the LEDs all compact, and you've got to figure out how to cool it. And you may have to add fans or heat pipes, and then the last people are even looking at using liquid. So we figured out for a traditional optic, you need about 8:1 to get a 15-degree beam. It says if I have a 3-inch source, I'll need a 24-inch optic. If I could do it in 2 inches, I could make that optic 16 inches. If I can get to the point where my LED is 1 inch, I can make this an 8. It's the concept of E10 The size of the source decides the size of the optic. You know this in cameras all the time, right? You have a 35 millimeter camera versus a 65. Lenses are twice as big. You go from an 8 to a 16 to a 35. The lens is scaled to the film, or to the sensor. Same is true of light sources. The size of the lens, the optic, has to be reflected in the size of the source. So here now we're doing optic simulations of all our products before we build them. And it reinforces the 1 to 8 works really well for a 15-degree. So what we learned about cooling, so I tried doing this, and this worked okay. I got some great pictures of this burning up, by the way. So we started like trying to pump the fluid behind the LEDs, but we just couldn't get enough. So we found out that we could submerge the LEDs inside the fluid and cool it from the outside and the inside at the same time. That allowed us to go a lot more intensity and keep the LEDs safe. Turns out that a cubic meter of air is about a kilogram. A liter of the coolant is about a kilogram. That's 1,000 to 1. So you've got 1,000 times more mass with a liquid than you do with air. So you've got to push a lot of air over something to cool it as opposed to liquid. That's why any car, anything with significant horsepower, had to go to liquid cooling. So we went the same way. So what we do now is we push 5.7 liters of fluid per minute through the center of the tower and around the tower, and then it goes to a radiator where we can then push the air through at 8,120 liters of air per minute. But that's away from the source, and it doesn't have to contact the LEDs. And so that's the basis for how the liquid cooling works. So that was our invention, and we're continuing to go down this path. Our goal is to do more and more intense sources in smaller and smaller sizes, and stay with kind of a more conventional single source large optic approach. So, does the fan make much noise on the set? The fans do make some noise. We are going to give users the ability to control that when they're shooting. There's enough thermal mass that we could probably cut back. Right now we use large fans that are deliberately quieter. So it hasn't been a big problem, but as a key light it becomes a bigger issue when it's right next to the camera. The pump was actually the bigger challenge. And so now we're working on soundproofing and reducing the pump sound also. But you can walk up to the fixture and hear it. It's very similar to other fan-cooled lighting fixtures. All of the fans are in that about 30 decibels. Yeah, and then you also get into the frequency of the fan too, and the frequency of the sound matters a lot to sound guys.
What is the liquid coolant? Is it like mercury, like computer?
It actually was developed for mainframe computers. So this cooling was made for mainframe computers and gaming computers. I love gaming technology. They've gone and done all sorts of crazy cooling. So we actually use the pump and fans from gaming computer systems. The liquid is a high-grade mineral oil. So we basically pay for really expensive baby oil. It actually doesn't taste bad. I've tasted it. It won't hurt you. It doesn't freeze. It doesn't evaporate. We wanted something that wouldn't boil or evaporate or freeze in the cold. So we went through quite a bit of a selection process to pick the coolant. So the one thing that I'm just going to throw out there, and I loved the area discussion on it because I think this is critical, is right now lighting is one of the last areas of control that's just really a matter of opinion. So the light's brighter, the light's less bright, the light is red. What's red mean? Well, it's not green or blue. There is no standard right now in lighting for what those colors mean. So it's just what the manufacturer makes. So if you get 4 different manufacturers and say, turn the lights on red, it's whatever the red they picked. Now, fortunately, they're usually kind of close, but there's no real standard in lighting control today. There's some options, people are looking at it, but it's not correlated. In order to get accurate color, now the other thing I'm going to say is, camera guys and the rest of our industry, they're very good about wanting accurate color, but they have dozens of standards too. There's not like one color standard that everybody uses to consistently. Each camera has its own color space. ASUS is proposing a few. So this is all the color spaces that are commonly used in our industry. So this is a big challenge. Now with virtual production, and we're doing a lot of work on that, you have an LED wall, you've got a camera, you've got a bunch of lighting, and you're going to play a plate. What those colors mean matters. When you say, I want this RGB color on the LED wall and I want it on the light to mimic the same event and I want the camera to read it accurately, that I see as an area where SMPTE and associations like this need to get involved in helping us derive a kind of more common and shared color standard. So when we say I want this RGB value of color in the light, on the wall, in the camera, we agree of what that color should mean. And there's some good work going on that, and I'd like to see lighting be a little more correlated and a little more industry standard controls so our colors start matching each other. But the first step, and I was glad to hear Aries doing the same thing, is we do color calibration using a color spectrometer. So on the back of all of our fixtures, you can plug a Seconic through the USB port, put it in front of the fixture, and say run, and it will run several dozen, depending on the light, up to hundreds of samples, and actually sample and play until it color correlates the instrument. And so our lighting has an auto calibration based on CAE color so that we can calibrate the lights, and you can recalibrate them in the field. Depending on the fixture, about an hour. And it needs to be in a dark room to do it. Yeah, so the ambient light doesn't affect it. On the smaller fixtures, we just stick it in a box, and that's how we do it. But we think the calibrated color is really going to be critical for lighting moving in the future. That you need to be able to count on what is the CIE XY values I'm going to get out of the light at this setting and have it be reproducible. All right, that's my presentation.
Thank you for my invitation to be part of your presentation. Just a couple of things to start. The two that preceded me, Brian and Chuck, I congratulate you on your technicality and such. I'm not going to repeat the same stuff, which I could have, but we also show that same CIE 1931 chart. I'm not going to do that. We're going to be talking about, as David said, the big shapes in the corner, on the side of the room. These are the muses of light. This is a joint design between the De Sistis and Vittorio Storaro. For those of you who may not be familiar with him, and I think you all are, Vittorio Storaro is probably one of the most celebrated filmmakers in our industry. I always use the explanation, 2 words, Apocalypse Now. Also The Conformist, and I believe that he has won 3 Oscars. So when he saw the need for a different kind of fixture, he, along with his daughter, Francesca Storaro, who is an architectural lighting designer, they approached Fabio and Sergio De Sisti of De Sisti Lighting in Rome, and working in concert with the Storaros, the De Sistis put their considerable design, engineering, optics, and manufacturing skills into the creation of a new light, or a new line of lighting for the cinema called the Muses of Light. Now, if you know anything else about Vittorio, he is part cinematographer, part teacher, and very much a student of philosophy. He's also kind of set in his ways. I've had the pleasure of meeting him twice. The first time was when he came to visit us at Shadowstone, a company that I worked at a few years ago. And my boss, Frank Marsico, said, I want you to get every LED that you can find, get it set up in the demo room, and I want you to take him through all of it. We wanted to be known as the specialty lighting rental house, and so I got all excited, thinking I'm going to have the undivided attention of Vittorio Storaro for God knows how long. And I went and I spent a week putting every LED I could find in the demo room, dressed all the cables, had it all perfectly set up. Vittorio comes in, sits down with my boss for about 20, 30 minutes. He really was coming in because he was scouting for one of the many films by Woody Allen that he DP'd. Came out of Frank's office after that, and before he went into the rental department to check out our inline 20K dimmers, Frank says, this is Paul, he's our VP of sales, he's got all this stuff set up for you. And Vittorio looked at me and he says, I only shoot in a tungsten. And my heart sunk. and I was not able to spend an hour teaching Vittorio Storaro. I couldn't believe it. Skip ahead a few years, I'm interviewing for the job at De Sisti. Fabio De Sisti happens to be in New Jersey for that. I'm meeting with my now boss and Fabio shows me all these pictures of this new line of lighting that they're creating called the Muses of Light. They're LEDs, co-designed by Vittorio Storaro. And I said, impossible. He only shoots in a tungsten. And Fabio, of course, he's roaring, laughing, and he says, you got to tell him that story the first time you meet him. Skip ahead another few years. We're doing the rollout of these things a couple of years ago, and I know you were there, Dan. We were at the local 52 stage in Astoria, and we did this whole rollout, and we had Vittorio Storaro in to do the presentation, and we're all out to dinner the night before, and Fabio wants me to tell the story, and I totally chickened out. Couldn't do it. I didn't know whether or not he would appreciate he only shoots in a tungsten accent and all that, but the bottom line is he is a genius. And helped us create this new line of lighting. There's 10 lights in the line. It's a departure from the traditional fixtures that we've all been using for decades. And they range in sizes from as little as a 14-inch aperture, which lives in one of the bodies of our standard 14-inch Fresnels, all the way up to that big 5-footer over there. And with beam spreads from as little as 11 degrees all the way up to 105 degrees. The key benefits of the Muses of Light, and what's funny is, you know, a perfect segue, the last two presenters kind of touched on a few of the things that I'm going to touch on, and I agree with you 100%. Very low power consumption. For example, that big guy, that 5-footer in there, it only consumes about 2,000 watts of energy, and it replaces large format projectors such as even it damn near as much output as an 18K or a 20K Fresnel. Variable white CCT control, which our second presenter talked on, correlated color temperature. The Muses of Light range is from 2,800 Kelvin all the way up to 6,500 Kelvin, and they can be controlled both locally from the power supply, which is removable right on the back, or DMX, also by wireless DMX via Lumen Radio, or I already said locally with a very high CRI of greater than 95. No high wattage lamps, obviously. The Muses of Light are powered at a very low power, considering their dimensions and their heat dissipation. The expected lifetime, as everybody has been talking about, is about 50,000 working hours without a perceptible variation in our color output. The other things that we do a little bit differently. We got 4 LED dots per point. So 2 of them are 2,700 Kelvin and 2 of them are 6,500 Kelvin. And they're on 2 separate dimming channels. So we can basically create any combination of color from that 27 to 6,600 Kelvin or 6,500 Kelvin accurately. The LEDs are all phosphors based. So our choice for going for phosphors based is to guarantee a repeatable, accurate color temperature, regardless of the age of the LED. This type of LED is very consistent and provides a very, very super stabilized white point. There was a question for the last presenter, Chuck, about fans. There are no fans in the Muses of Light. Later on, when we get up and we go and check it out, you'll see that the entire back of the product is a giant heat sink. Okay? Same thing with the power supply. Heat sink on the power supply, 0 fans, so there is 0 noise. You know, I skipped over it there. Basically, one of the things I was going to talk about was the fact that you can operate these things in very humid environments. The Muses of Light have no problem working in extreme humidity like that. Optically, optics is probably Fabio De Sisti's strongest skill. The optical system that we utilized for the Muses are varied to obtain the choices of beam angles that we need. And as David said, there are 10 lights in the line. Each light in the line has a different beam spread. In some of those lights, we use lenses and collimators, which are optimized for the layout of the source. Those are the ones we use for the 11, 16, 28, and 34 degree beam angles. In some of the other lights, we use reflectors and diffusers in order to get the beam angles that we want between 66 and 105 degrees Kelvin. Each of the Muses models represents the best possible efficiency for their optics. So in fact, that's the reason why we've adopted the fixed optic criteria. We don't have a focusable light. 10 lights in the line, you use the correct light for the correct beam spread that you want, and we get the most efficient output based on the shape, the size, and the LEDs. Much better than we could with a variable optic system. Okay, so I'm going to just go through these really, really quickly because I want to spend a little bit more time over there actually demonstrating the lights, because right now they're all at about 5%. And I could do a decent amount of lighting in here with just them at 5%. But when I crank them up, I think you'll be really impressed with what they can do. The first light in the line is the Melpomene. That's the triangle that you see over there. As you can see, it's a narrow spot. It's 11 degree beam angle, and I'm not going to read off all of the photometrics and everything, but at 5,500 degrees, you're getting 555 foot candles at 10 meters. That's 33 feet. The next one is the square, the tersicore. The tersicore is a 16-degree spot that'll give you 5,500, or I'm sorry, 998 foot candles at 5,500 degrees Kelvin. The Clio is the rectangle. That is a 16-degree beam angle, and will give you 499 foot candles at 5,500. The Polymnia is the pentagon. This is one of the first of our floods. So this one is a 28-degree beam angle and will give you 35 foot candles at 55K. Dorado is the hexagon. That's the next flood. It's a medium flood at 34-degree beam angle with an output of 90 foot candles at 5,500. Euterpe is the octagon, and that is, I just realized a bunch of my slides were skipped over. Son of a gun. All right, so that one gives you 45 foot candles. The Thalia, which is the decagon, is the 105-degree super wide angle. That will give you 95 foot candles at 5,500 Kelvin at 10 meters. And after I show you that, I'm going to just put some pictures up here to show you what these things can do. The Aurea, which is our big guy there, that gives you a whopping 68,465 foot candles at 10 meters. That's just a little over 2,000 watts of energy, and puts out an incredibly focused beam. And one of the things that a lot of our, actually, let me just go through this really quickly. I'm going to just jump over here if you want to follow me here. I'm going to start with the Melpomene. Like I said, I've got this guy at 6% right now. So I'm going to crank this guy up. Let me knock the other ones down for a second. Knock him down. And knock him down. Okay, so Melpomene is an 11-degree beam angle. And by the way, if you're wondering about the shapes and such, there are two schools of thought. One of them was proposed by one of our customers, who is a very well-known gaffer here in the city. He felt that that was the large pie. This is the Brooklyn style. This is the slice, and then the Clio, which is the rectangle. That's the Sicilian. But anyway, now I'm at 100%, and let me just loosen this a little bit. So, whoop. Here we go. And we can see how tight a focus beam we have there. Okay. Right now I'm at, come on, I'm at 2,700 Kelvin, and I could take that all the way up to 66 or 6,500. Even though this is a multi-point source, obviously, I'm casting a single shadow. Okay? And even though this is a spot, it falls softly on the subject. That's one of the things that a lot of the gaffers and DPs really love about this is it is a spot with a defined beam, and I can walk in and out of the beam just a couple of steps. But the light falls on your subject softly. If I move over to my next light, come on. Down some more. Move over to this one. This is the Tersicore, which is a 960 watt light with a 17-degree beam angle. You can just see how much light output you can get. And this is just going into a standard 20 amp circuit, but I could plug this into a 15. Not a problem. Not a problem. And what I was talking about before, I'm going to turn this around so you can see it. The entire rear of the Muses is just one giant heat sink. Okay, so the way that they're constructed, and I'm going to turn this one up a little bit so you can see it a little bit better. And I've got this one. You can remote the power supply up to 150 feet away, and like I said before, you can work it in either DMX or wireless DMX with Lumen Radio. Just turning this up to 5% again. The construction is such, you probably notice that everything is modular. Okay, so on the board itself, you've got triangles, You've got arches, and then you've got straight shots and individual LEDs. So for servicing and things like that, it's not like the whole thing has to come apart. We can just take the individual section that we need to if there's an issue. Let me crank this up so you can see how powerful this guy is. All right, now I'm at 100%. And let me loosen this a little bit. Just take a look at what kind of output you can get with a little over 2,000 watts. I wish we had a bigger room because it's really impressive when you see how long this thing can throw. So there's our, the construction of these is such that the LEDs are chip on board. They're mounted directly to an aluminum plate, and then that plate is sandwiched between the heatsink and a sealed front cover. While we are not 100% IP rated officially, we have performance capabilities as good as an IP23 fixture. So the thing can live out in the rain, okay? That's why it's had no problem with the humidity inside that cave at 98%. Just a couple of images from the factory showing the construction of the fixtures. And you can see how it works. This is what I was talking about, where we've got just the big aluminum plate, the chips mounted directly to that, and then sealed on the front. Some more images there of some of the collimators that are on the Aria and the Clio here in the lower right. Just some more images. Enough of the images. Let me just show you some of the great uses for the. Oh, by the way, there is one that I didn't touch on, and that's this one here. That's the calliope. The calliope is something that lives inside one of our 14-inch Fresnel bodies. And instead of a Fresnel lens, it actually has a Plano convex lens on the front. This is something that Vittoria wanted to use as a drama light. And its purpose is to basically give you a hard edge at any distance and at any focusing, or at any focus range. So it really is, it's a cool light to see, but unfortunately I don't have any here in the States yet. Okay, just some images, outdoor use. This is from Rifkin's festival. This is one of Vittorio Storaro's works with Woody Allen. There he is. Okay. As far as doing architecture and such, this is something that his daughter did. This is for the inauguration of the Rhinoceros Palace. Don't know where that is. I think it's in Rome. But you can see the Aurea being used to light the rhinoceros there. Some other there. This is a great image in the back of the DeSisti factory. You can see this one light and what it is able to do. The DeSisti factory is long, and one light is providing all of that output. Same thing with the Melpomene. Okay, and then one of the things that when we first started talking about these lights, people automatically start saying, well, what's it equivalent to? Is it equivalent to this? Is the 1K, a 2K, a 5K, whatever? We stopped answering that question because it really is, it's an apples to oranges comparison, okay? The lights are completely different than what everybody's been used to. So we basically are in the habit of putting them in the hands of the filmmakers, and they find different uses for them. And this is a perfect example of it. Simon Ray needed to create a sunset where a sunset was not going to happen in nature. We actually were showing this picture to people, and they didn't believe that it wasn't the sun. So we actually had to have another angle to show that it was done there. This is one where they're doing some tests, trying to figure out how it would look next to an actual image of the sun. And it's incredible what some of the applications have been come up with by some of our customers. This is an image showing rigging on the outdoors being blasted through the window, and as Steve Ramsey had said, this is a perfect example of the light being a focused beam but still falling softly on the subjects inside, and that's something that we really have not seen in any other light without a ton of light shaping apparatus. There's another image there. Okay, this is using the Euterpe with umbrella diffusions inside some place in Rome. I can't remember what it was. Some DPs actually like to have them in the frame because of the unique shapes. They actually look cool as part of the frame, so they've been actually using them that way. This is an image of the Taglia, which is the 105-degree beam angle. This was actually a production in Italy. It was actually a Christmas program. It was called Holiday on Mars. But they're using that one light to create the base lighting for this whole Mars set. And then just other images back behind the factory showing the power of the Aurea. This is actually one of the first prototypes where we actually had 2 power supplies on it. Now we're in 1. And then finally, an image of Pope Francis being lit by the muses of light. And we figure if it's good enough to light the Holy Father, it's good enough for lighting any of us. So with that, I will say thank you. If you have any questions, I'm ready. The muses were all named after the nine Greek muses, the muses of Greek mythology. And the 10th was actually created by Vittorio. That's the Aurea, which he calls the muse of cinematography. All the muses are the inspiration of all of the arts and sciences in Greek mythology. Each of those is tied to a specific geometric form. So that's why he came up with the different shapes. It truly is a matter, as he'll tell you, it's a matter of interpretation as to what you think of the shape and how you're going to use it. Keep in mind that even though it's a triangle or it's a square or it's a circle, all the beams are circular, okay? Unless I'm right on top of the wall, it'll look kind of triangular on the Melpomene, but it is a circular beam. Again, it was just a matter of his interpretation of the muses.
I'm Mitch Gross. We are a fairly young company. It's been around for about 8 years, but it's only been in the international markets. It was a Chinese-based company, even though it has a Germanic name. It's only been in the U.S. Markets for about 2 years now. And I'm going to present without actually not running the slide, because that way I can zoom in and out of things, and I like to show certain things. One of which, if I can just do that real quick, I'll just, these 3 young ladies, or it's actually 1 young lady, lit by 3 different lights, 3 different, we just switched on and off the lights that we had lined up and got 3 different images. And if you look, her skin tone is quite different on each one. That's why I like to zoom in, so you can kind of just look at her face, look at her skin tone. But all of these lights had not only very similar high CRI, but high TM30, high TCLI. Almost all these scales were very high. And it shows that a lot of the numbers that you heard tonight, I know that we're a society of engineering and like to believe in numbers, but numbers don't tell you the truth, at least not yet. We don't have the most accurate systems yet of truly measuring all aspects and quality of light and color, so that you could have lights that hit those scores and hit those numbers and actually match. Because you can see, they don't really match, even though these lights not only claim from their manufacturer, but actually when we tested, based on what those numbers, and the standard measures that you use, they, allegedly matched, but they don't really. So a lot of this is alchemy. It's a lot of special sauce from your manufacturers to get to where you want to get. And I'll get into that a little bit more with the charts that everyone's already shown, and I will show as well. Before I do, I'm going to say that little cluster on the right side, that is what our actual cob looks like, our chip on board. COB, chip on board, looks like. So if you dug out the inside of that light, you would find that deep within it. So there it is. There's that same chart that we've seen several times, CIE 1931. And what I want to talk about, first I'm going to talk about what color technology is. And a lot of this has been covered, so I'm going to kind of skip past things real quick and try to get to the heart of what's important here. This is your 1931 chart. Let me just move that up so you can see it pretty large in here. And when you're looking at this, everything, that big kind of jelly bean shaped thing, that's visible light, right? That's what the human eye can see. This is your color temperature range right there, your black body curve, as it's called, and such. And so this represents white light, but white light burning at different color temperatures. If you lit a match, it's pretty low temperature versus if you, the heat of the sun, that's going to be a much higher color temperature. But it's all colors of the spectrum are represented. So, where this is very, very green, this is very, very blue, and very, very red, in the center, it has all of the colors of the spectrum, and they're mixed. You get the full range of colors. And so this is desaturated, right? Because you have all the colors, versus this is saturated in the direction of blue, this is saturated in the direction of red, right? So that's the different. That's what you're defining here. So imagine this is a two-dimensional representation of what is a three-dimensional charting and such. So you can imagine this is a big blob kind of thing. Anyway, if you look at this little red line, if you guys can see that little red line, I don't know if you can really pick it up there. Right here is 3,200 degrees, which is tungsten light. Right there is 5,600, and what you get is you have a curve, right? Well, if I have a bicolor light, a light that has a warm white LED and a cool white LED, and at warm white, okay, maybe it's going to be at 3,200 degrees and it's going to be on target and the colors match pretty well and stuff, and at cool white, it's going to be pretty accurate, but when you go between them, you're not really following that curve. What you're doing is you're just dimming one side versus the other. So you're mixing these two, and what happens is it doesn't travel in the curve. It goes in a straight line. And if you look at that straight line, you see it dips away from green, and the opposite, a lack of green is what is magenta. Magenta doesn't actually exist in reality. It's a lack of green. So you go negative green. And so a lot of bicolor lights, you will see that when you adjust that, when you go to like 4,500 degrees or so, somewhere in between, which a lot of people do when they're in like mixed color use space and stuff, they want to kind of go somewhere in between so they can match the things, you'll see your lights start turning a little bit magenta. And the camera, your eyes might compensate for it a little bit, but your camera doesn't know to compensate, and things will start going magenta. So this is very much a limitation of what is a standard bicolor light. Now, a monocolor light is just one color, right? Just daylight. Well, what you're doing is you're asking a single LED to do all the colors of the rainbow, right? All the colors of that chart. And so if you are a monocolor LED, well, what does it do? It's actually like going to be burning at like, some super blue sapphire or something, whatever. And then they put a bunch of phosphorescent material on top of it, various grains of chemical and goop and stuff that they put on top. And it's the old how many angels can dance on the head of a pin. You can only get so accurate with this gooping that you put on top of a given single LED, and then you're going to have a whole bunch of LEDs that you're going to have all gooped the exact same way. They're going to have certain deficiencies. We've gotten much, much better over time, but you're asking one LED to do everything, and so it invariably will have certain deficiencies. And you'll really see those deficiencies as you dim it. So this is where some of the other manufacturers were mentioning that as you take these lights and you actually dim them down, you're going to start to see shifts and how they perform, because these different phosphors and such might start changing as they dim down. Well, so here's an advantage to having a multicolor array, right? Like, we are up in the corner here, red, green, blue, amber, cyan, and lime. That's our mix of 6 different colors. You can think of 3 different benefits to that. One is that you're not asking any one LED to do everything. If you look at the chart here, here's our 6 different targets: red, green, blue, amber, cyan, and lime. And so, this one kind of does this zone, and this one does a whole bunch of this zone and stuff. So you're only asking them to do certain amounts of certain parts of the color range. And because of that, they can be far more accurate. You're only asking them to do this much work, and so they can be much, much better at it. You can do, whether it's a chemical dye or phosphorescent material put on it, it's more accurate to cover that range. Yeah. It's just because they're overexposed when they were photographed. It's red, green, and blue, yellow, amber, cyan, and lime. So it's probably the cyans are coming up like that. It's an overexposed photograph. So anyway, advantage number 1 is better color accuracy. And we cover the entire range. It's just that we do it in sort of blobs. This one covers this zone, and this one covers that zone, and together they cover the whole dang thing. The next greater efficiency is in brightness, because if you put lots and lots and lots of goop onto each LED in order to get that whole range of color, well, you're putting a lot of gunk in front of the LED, the actual emitter, and so it can only glow so bright. So you actually get more lumens per watt by doing it this way. And you get greater brightness because you are not, like compared to a bicolor light, if you want to have, say, 3200 degrees, well, you're going to have half the LEDs are going to be turned on, and the ones that are the cool white LEDs, the bluer ones, they're just going to be turned off. And so you're going to have way less output from that light fixture because you're not using half the LEDs. Well, we have all 6 of these are always, unless you're going for some super extreme color, if you're going anywhere on this curve, certainly, you're going to be using all 6 LEDs. You're just going to be balancing how much of any of them that we're going to use at any given time. This is a 675 watt light, and that the limitation of 675 watts is with our power supply. And what we did is that each LED actually has the capability to go well beyond. If you powered all of them together, they would go well beyond 675 watts. And the idea being that at any given time, you're going to get the maximum brightness balance for whatever color temperature, whatever color setting you might choose, based on how you sort of dance those 6 different colors. Yeah. So the question is, how much work is the amber doing, since you have red and you have lime right here? Why do you really need amber? Well, it's because it's where here's my skin, right? Amber is where we are extremely sensitive to things and where we want in our lighting, because we light a lot of human beings, and it's where we wish to fill in as much richness in color as possible, because we are very, very sensitive to that in what we photograph. Yeah. All right. So basically, the idea, for the video people watching at home, the idea is that you need 6 colors because you need to fill out your spectrum fully. Because if you just had, say, red, green, and blue, in theory, when we learned color science theory, as kids and whatever, we were told that red, green, and blue together can make white. They can make all the colors of the rainbow. Well, not really, because it doesn't cover everything. It's going to have parts of that range that kind of drop out. And so those areas where these emitters, these colors would be weak in their coverage, that's specifically where we didn't randomly choose these other 3 colors. We chose them based on where you have deficiency. It's kind of equivalent in the video world of primaries and secondaries. It's not exactly the same, but it's kind of equivalent to that. And so, there's amber, and then there's cyan, and I'll show you in a spectrograph, a spectrum later, that cyan is where most lights are really weak. They're terrible, and they just have a big dropout. And so we actually bump up in cyan because, well, you need cyan. You just want to be able to get that. And so the last way in which this is a better way to go is that you just get way more range of color than you would with other systems. You have a vast range of saturation and color that you have capable. So you have better power, you have more output, and you have greater range. So let's compare to another technology, which is a little bit older technology, which is RGB-WW, red, green, blue, white, and white. And sometimes it's warm white, cool white. Sometimes it's an R or an AW, which is a red, or an amber, which is, sometimes they'll have a color right there, which is similar to our amber. So here is a red, green, and blue, and then there's your warm white and cool white. And then sometimes instead of the warm white, what they'll do is they'll put this amber, and they'll say, oh, okay, that way we can fill in that part of the range there. Well, if you look at what this triangle describes, it's a far smaller triangle, a far tighter range than what this one does, what this range does. This kind of sort of pushes out a little bit here, and it pushes out a little bit here to give you a far broader range of color. Deeper saturation is what you're getting here. Deeper saturation and better accuracy of colors in your limes and in your cyans, which is very important because we don't get that here. I mean, like literally, if you had a Pantone color chart and you had something, your client had a product, and the dress had to be just this right color and stuff, and it so happened to be this saturated thing, guess what? Ain't gonna show up, or ain't gonna show up accurately. And that's where you want to be able to cover that part of the range, with any kind of real saturation. So what a lot of these RGB WW lights are is they're really a bicolor light. They're warm white and cool white, and then they augment with red, green, and blue. They fill in parts of the range to get a little extra saturation stuff. But if you really wanted to get, say, a deeply saturated green, you're going to start turning down the warm white, cool white, and then first off, your skin tones and such are going to go to junk. They're going to be looking terrible because they're just not going to have filling in of the whole spectrum. And the other thing is that the RGB part of it on most of these lights is actually quite weak. They'll be several hundred watts on each of these, and then just a few watts relatively on those, because they're kind of really designed to just fill in. And then it just means that you're going to have a very dim light. It's not going to be very effective, and it's not going to have the best color in the world. So this is, in fact, something that there's a lot of studios being built for these virtual studios where they have these big LCD walls, LED walls that are these virtual backgrounds they put in, and people are thinking, oh, nobody needs the light anymore. It's kind of like when the first Sony HD cameras came out, and they Peter, are you still here? They were going, hey, nobody needs the light anymore because the cameras are so sensitive. Well, and they're saying, oh, nobody needs the light anymore with these virtual spaces because the backgrounds, the backdrops that you see, well, that's going to light everything. It's just going to shine onto your talent in front. And, it's coming the wrong direction, for one, but also it's just not true. And even when it does give illumination to people, it's not very good color because it's just red, green, and blue on those screens, and they have poor spectral distribution. They don't cover the, richly the full range, and therefore skin tone looks terrible. And what does everyone have to end up doing? They just bring in lights to go and fill in on the talent and such. So here we have RGB ACL light, and that is filling in with very rich colors. So we actually can take one of those signals and we can become like a virtual pixel and stuff that's being used in these studios. And these are becoming extremely popular in those studios for this exact reason, that we can take an RGB number and replicate a full color spectrum of light that an RGB light itself can't do very well, or panel. Does that make sense? Hopefully. Okay. So there's lots of different kinds of spectrums that you want to try and match, and there's different ways to do it. This is just sort of, there we go, just showing you different ways that you can, that what different spectrums look like from different types of emitter sources and such. And there, by the way, there's a regular white LED and what it's doing. And like, look at the far red, like dead. But also, there's cyan. Look how weak it is. Well, if you're gonna do, a lot of people don't like to go full blue for their moonlight effect. They want to go something a little bit different. They want to go cyan, and so it just feels a little cool without it being that full kind of bluish look. The problem is that most LED fixtures don't output cyan well at all, and it just gets dim, it gets weak. And so we actually are far, far better at outputting that cyan because we have a cyan emitter. We can just set the light to cyan and boom, it's nice and bright. So this is just to show that if you only have 3 points of light, you can adjust them a little bit, and then if you take warm white or cool white and you add it, what it's just going to do is just going to desaturate the image. It's just going to raise and lower everything. That is the 6 different colors that we had, right? That we can control those 6 different colors, and that would give us, fine tuning of that color spectrum, of the whole visible light spectrum, and so you could really tweak that to whatever color you want to get out of it. What does this mean in actual practical terms? And this is where I like to go over to light to show you what was an actual practical fixture. First off, I hope you notice that this kind of looks physically like traditional lights, like a regular light fixture. Now it has our Fresnel on it. We don't, that is an accessory to it. You can take that off and you put other things on the front, like a projector, like we were seeing on the orbiter there before. You can put soft boxes, and we have a bunch of things. We have a partnership with Datolight, and they're developing a bunch of optics for us and such. So this is our Fresnel, which is 15 to 50 degrees. You can see we have a nice clean beam out of it. And I'll talk about that more in a sec. But we have a color temperature range of 1800, so very warm, all the way up to 20,000. So it's actually it's the biggest range in the room. It's the biggest range in the industry. 1800 degrees to 20,000 degrees. And I can do the whole thing that we were doing with everyone else. Like you can do the dimming and get down to 0.1%. It's extremely accurate, throughout the range and all that stuff. But we can get there very quickly and easily. One of the things I do like to show, though, is I'm just going to switch modes and stuff. And it's a very intuitive little menu control, and you can control it on here. You can control it, through wireless things, whatever. I have an app on my phone I can use, which I'll show you a thing on there in a second. But one thing that's in here that I think is pretty nifty is I'm going to go to our gel equivalent mode. Now, gel equivalents are literally, if, back in the day, if you wanted to change the color of your light, well, what'd you do? You took a piece of gelatin and you put this sheet of plasticky stuff in front of a light, and it was whatever color you wanted it to be, and that's how you change the color of the light. Well, we've programmed in 300 plus different gel equivalents, both for from Roscoe and Lee, and it's a little menu in there, and it's divided into different types and stuff. But what I did is I programmed in Lee 101. So I set the light to 3,200 degrees as a base, and then I put on Lee 101, which is yellow. And let me tell you that good luck on using any other lighting technology to get a yellow that has anything like that accuracy. Because if you're just an RGB light, what you're going to do is, you don't have this miracle of lots of different colors that are, you have red, green, and blue. And so you're going to take red and green and you're going to dance them off of one another to try and shift your way towards yellow. Well, good luck on that control. You're going to end up with something that's either looking a little orangey or a little green. This is an extreme, I'm pointing at black, so it's kind of hard to tell, but this is an extremely accurate, rich yellow. And it's nice and bright. You know, the only other way to do this and to get a yellow is with an old-fashioned, you know, like tungsten light and putting a yellow gel in front of it. And you're just not going to get there. So and I'm happy to put this up against any light you want, and you can see that you just can't do it. Now, there is the XY coordinates, and you're going to see that you can get that, you know, the CIE chart that we were looking at before, right? You can have, we have it in here. I can go to the CIA, right? You see that same chart right there, right? And I can go with XY coordinates and such, and this is where, you know, someone was saying before, it's like, you know, it would be really good to have, you know, a standard that everyone can follow, and then, you know, you can agree on what these things. Well, guess what? You would think if you have that chart, and you can go down to 4 decimal points of, you know, like, you know, exact coordinates of X and Y, where these colors would be, you would think, okay, we're scientists, we're engineers, we're technical people, that's a very precision number, and you're going to get to that point, and that's going to represent an exact set of frequencies to deliver. Wrong. Because it depends on how you get there. You're mixing, in our case, 6 different colors in order to get yourself to that target. Other lights are going to be doing it in other ways. They only have so many controls. You basically just have these 6 different color emitters, and you're going to, I mean, we have many of them, but, you know, like a dozen or so of each color. But you're going to be taking those things to try and land at a certain point, and maybe you will, maybe you won't. It's how accurately you get there. You know, there are many ways to skin the cat, as they say. So how accurate are you going to get to some of these colors? What is that performance going to actually look like? It can vary wildly between these different lights. So, other things to show you with this. I mean, like I was saying, this looks like a traditional fixture, and there's a reason for that. Because there's the thought of, here's a new piece of technology that this can change the way you work. Or you can say, you're comfortable working the way that you work, and let's just make life easier for you and better for you. So let's give you what is the equivalent in output at 675 watts of a 1200 watt HMI or a 2000 watt tungsten Fresnel fixture. These are common lamps. People know that it's basically the same form factors and size. And yet, okay, we're going to give you the equivalent to that, but if you want to change the color to anything you want, here you go. And you're going to use much less power. And it's not going to output any heat. And you can put it out in the rain and let it let it run in the rain. And you can dim it without it shifting color. And you can, you know, run it off a battery if you want. Run it off a battery. So, oh, yeah. HSI mode? Yes. Yes. So we have many different modes, and that's actually another thing I wanted to talk about. So,
Explain what that mode is.
yes. HSI is, yes. So we had CCT, the comparative color temperature, where we went to 1800 to 20,000. We have an HSI mode, which is hue, saturation, and intensity. If you look over here, you see that ball, and that's if anyone does, like, you know, After Effects or Photoshop or whatever. That's, you know, it's literally, I can go in here and I can rotate this knob, and I'm going through all my different hues. So if I just want to quickly get to a certain kind of color, you know, I can just go and find it like that. And then I can adjust how saturated I am at any given point with that. So hue, and then saturation, and then intensity is just brightness, right? In any of these modes, we have an indicator that just tells you what the XY coordinate is, so that you can go to an XY and you can replicate that. You can also, in any of these modes, hit this save button, and it will save whatever that setting is. We have a separate page of like all the presets, all your saved things, and you can just save that, and so you can use that to pull it up later and match it and stuff. And when you save it, it saves every single parameter that you've just done. So even to the point of having saved how bright you had it set to, right? It was you're running at 30% or whatever. Everything is saved, and it tells you in a very graphic way, so it's very straightforward. We also have, in our different modes, so I told you the CIE chart, then you can go and actually put in your XY coordinates and just find it right like that. I have your gel equivalents. We have source matching, so we just went and profiled fluorescent lights and sodium vapor street lamps, whatever. We have 40-odd different of those that we just, so they're presets. You can always create your own, but we just had it preset. Yeah.
You might point out.
Yeah, gels will fade. Right. When you're putting a gel in front of a light, right. So when you're putting a gel in front of a light in order to adjust its color, what you're doing is you're blocking everything that's not the color that you want, right? So I mean, it's going to cut down the brightness of the light. It's also going to be absorbing all this heat from a lamp, and so in absorbing it, what will happen is that gel will usually just fade over time. So there's only so much, and you know, it's also, you get one batch from, you know, that was manufactured this time, you get another batch that was manufactured that time. How accurate and consistent do they remain? There was a great story of Gordon Willis would never use quarter color temperature orange because he felt that eighth color temperature orange doubled up was a more accurate thing, and so drove his lighting crew nuts, but you know, that's what he did. So yes, when you are using this light, what you're doing is you're just adding the intensity to certain frequencies, because we're using all 6 colors. You know, when I'm in yellow, how much blue am I using? Not very much, but I am using a little bit of it because I'm making sure that I am filling in my spectrum, so I'm not just a certain frequency and everything is dropped to 0. I am a soft, gentle hump towards that frequency, so that therefore I have better richness in color.